Okay, good. All right.
And if you move the slides, does it move?
Yeah.
Okay, good.
And then you can see my own stuff here. Okay, good. Perfect. All right. This next.
Okay. You got it? Okay, welcome everyone. Thank you for coming to hear our brilliant junior undergraduates talk about their research projects. So just to give you an idea, this is one of the courses in the department. It's called Astronomy 98, and a big part of the course is a research project. Each student works with an advisor on a real research project, and then they give presentations, they write a junior thesis, all of which will be evaluated. They have just had 2 months to work on the project, which is really not very long when you're doing research. So I think you should keep that in mind when you see the amazing amount of work many of them have done. They've been doing this at the same time that most of them are doing 3 other courses, right? So it's 1 course out of 4 in the semester, and I am blown away. And I am the professor. I've been watching these people for 2-3 months now. Amazing. We will start. Oh, I should mention, I have not arranged the talks by topic. I just used a random number generator and simply put students. So you'll find topics all over the map. That's okay. Nobody will feel victimized, if their name starts with Z or their topic is cosmology, and they say, why should cosmology be at the end? Nothing. This is random number. They get what they get. So our first speaker is Aurelia Balkanski. She's been working with Karin Oberg and Elettra Piacentino, and she's going to talk to us about some laboratory experiments.
Okay. Amazing. All right, well, for my junior thesis presentation and work, I worked on laboratory characterization of interstellar ice analogs of benzene and its derivatives. Specifically, the derivatives I worked with were toluene, phenol, and benzonitrile. So first, just a bit of background. Benzene and its derivatives are a very important class of molecules with particular characteristics that are really special to prebiotic chemistry. So we want to be able to understand these molecules and the chemical pathway for how they formed, because they later led to biomolecules and things like DNA, RNA, proteins, essentially the building blocks for life. So currently, we understand that a lot of these building blocks and these molecules came to Earth through comets and collisions that happened during the early bombardment period of Earth's formation. And there's a lot of literature detailing discoveries of these molecules on comets like the ones that may have once hit Earth. However, recently, benzonitrile was discovered in the interstellar medium, so essentially the clouds and the matter that will later condense to form planets like Earth. And so this leads us to believe that some of these molecules, such as benzonitrile and other derivatives, could have actually been accreted during planet formation and thus been present in Earth from the start instead of coming from comets. And so because benzonitrile is a derivative of benzene, we know that in order for benzonitrile to have formed, benzene should have probably also been in the interstellar medium. So we are going to look for benzene as well. And additionally, if we have benzene, we may have some more of its derivatives. And finally, with the recent launch of JWST, we have 10 times more power to look for spectra in space. And so there's been a huge push to kind of look for more molecules of this type. So why benzene and its derivatives specifically? Well, these molecules are special molecules known as aromatic molecules, which means that they possess a ring of electrons that are very important for prebiotic chemistry. So both DNA and RNA have aromatic structure, and all base pairs have this ring of electrons and aromatic structure. And so first, we can see here this model of benzene, which consists of 6 carbons, each bonded on one side by a single bond and on the other by a double bond, and connected to a hydrogen. And then in the second image, we have what is always there but not always depicted, which is the rings of electrons above and below this molecule. And essentially, these electron clouds allow the electrons participating in the bonds to actually move around the molecule and jump back and forth, which results in about an even distribution of electrons on either side of the molecule. And this makes the molecule much more stable, and it gives it these special characteristics that make it very important for prebiotic chemistry. Additionally, with benzene, what we show here is one of the most intense vibrational modes of benzene. And so when we view benzene in the IR, this mode, this kind of stretching of the hydrogens, shows up at a certain wavelength that is characteristic to benzene. And so when we look at a spectra of benzene, we can tell, okay, because of this wavelength and this spectra, we know that that molecule is benzene. So here I have an IR spectra of benzene, and we can see the 2 main peaks corresponding to vibrational modes in the molecule. And so benzene and its derivatives specifically, as I said, they're aromatic molecules. But they differ in their functional groups. And their functional groups are essentially the additional group of atoms in place of one of the hydrogens. So first I have the more detailed depiction of benzene with all of the carbons and hydrogens shown. But more commonly, benzene is depicted as it is in this red circle here. And we can kind of use this to compare it to its derivatives and see how they differ. So in the case of toluene, toluene differs from benzene in its functional group, which is methyl, due to the CN3. For phenol, there is hydroxyl, or OH. And for benzonitrile, the functional group is nitrile, or CN. And the presence of these functional groups will really change how the molecules interact with radiation, such as infrared radiation, infrared spectroscopy. And it will also change some of their general properties of the molecules, like their volatility. So how do we actually view these molecules in ice form in the IR? Well, we do so in the Oberg lab, in the vacuum chamber. So essentially, this vacuum chamber depicted here mimics the conditions of the interstellar medium. So it can be cooled all the way down to 10 Kelvin and heated up to and actually through 280 Kelvin. And additionally, it is kept at a pressure of about 10 to the minus 9th torr, which is significantly lower than the 800 torr that we typically experience here on Earth. And in this chamber, we can run a couple experiments, one of them being IR. And so with the IR, we want to find the signature and the spectra that is characteristic to the molecule that we are studying. And additionally, we can do mass spectrometry using the quadrupole mass spectrometer, which tells us a bit about the phase temperature of the molecule. And so knowing at what temperature and at what location in the interstellar medium, what phase the molecule might be in. So the way we run these experiments is first we cool the chamber all the way down to 10 Kelvin and pump gas into the gas line, so either benzonitrile, benzene, toluene, or phenol. And then we dose the gas onto the substrate in the chamber, and because it is so cold, the ice immediately forms, and we can take IR spectra of this molecule in ice form. And once the spectra is taken, we can begin to heat this ice on the substrate at 2 Kelvin per minute, essentially mimicking moving closer to a star in the interstellar medium, probing what the molecule will look like at different temperatures. And during this heat up, we take temperature program desorption data to find out, of course, at what temperature the molecule sublimates. And we heat all the way up to 280 Kelvin to make sure it is fully desorbed. And so first, as I said, we take IR data. And this is a spectra of benzene that we have from some of the data that we took depicted here. It looks the same, although similar for the rest of the molecules, which I will go into on the next slide. But essentially, we can see here we have 2 main peaks that happen in benzene. And the one we used specifically for this research was the peak right around 1500. And what we do is we can take the integral under the curve, and we can integrate that to get the ice thickness using the molecular band strength. So essentially how this works is the intensity of this peak in IR is proportional to the number of monolayers, or the ice thickness that is created on the substrate. And the band strength is the proportionality constant specific to this band. And so we chose the band right around 1500 specifically because in the literature we only have found only the band strength of benzene has been previously reported, and we don't have the band strength for benzonitrile, phenol, and toluene. And so we take the 1500 band because this band actually shows up in the other 3 derivatives as well, and so we can use benzene's band strength and apply this number when we do the calculations for the other molecules to make up for the information that we don't have. So here I show IR spectra for all 4 of the molecules taken at 10 Kelvin. And we can look at some of the similarities and differences in between the molecules, so we know if we have a spectra like this taken from space, we'll be able to identify which molecule it is associated with. So as you can see here, we have the band at around 1500 and another band at around 700 for all 4 of the molecules. And first, we see toluene and benzene are the most similar. But the way that we tell toluene apart from benzene is that at the 1500 peak and as well at the 700 peak, this peak is actually split. And this peak originally comes from the vibration, or from the stretching of the carbon bonds at the 1500 and out of plane bending of the hydrogen bonds for the 700 peak. And we see that the functional group in all of these derivatives kind of causes the peak to split and shift slightly. But additionally, for phenol and benzonitrile, we have other aspects that can help us tell it apart from benzene and notify that this is that spectra. So for phenol, we see a broad OH band, and for benzonitrile, we see the CN band peak that we can use. So now if we're looking at a spectra, we can say, oh, this one looks like phenol because of this broad band here. So then once we take our IR data, we can then begin to heat up the spectra. And for this, we take temperature programmed desorption data. So this is when we heat it 2 Kelvin per minute, we want to know when benzene or when the molecule sublimates and changes from solid to gas phase. So we can know in the interstellar medium what phase we'll expect the molecule to be in. So here, if we look at the temperature programmed desorption data of benzene, we can see that the highest peak is around 150 Kelvin. So we know that at temperatures higher than 150 Kelvin, benzene will be in gas phase, and lower than 150 Kelvin, we expect to find it in ice phase. Additionally, we can also fit a curve to this first bump here to find the binding energy. And this first bump is the sublimation of amorphous ice into crystalline ice. So essentially when the molecules just begin to heat up and move enough to start switching from ice into gas phase. And here, this binding energy tells us the amount of energy needed for that change to begin to happen. And we use the equation depicted there to fit this curve and find the desorption rate. And in this fitting, we are fitting for both the pre-exponential factor and for the binding energy. And we do this because the pre-exponential factor depends heavily on the uncertainty in the ice thickness that we measure, whereas the binding energy is not so affected. So from this, we can actually draw conclusions about the uncertainty of the binding energy versus the pre-exponential factor. And so here I have the TPD for all 4 of the molecules. We did multiple experiments for each molecule, individually calculated the binding energy for each, and then took the average, which I'm showing here. So as we can see for benzene, it desorbs at around 150 Kelvin, and its binding energy is at around 550 Kelvin. And then on the other end, phenol has the highest desorption temperature at about 200 Kelvin, and its binding energy is almost 8,000 Kelvin, as we can see here. So this shows that binding energy and desorption temperatures are positively correlated. And then to kind of bring all this into a summary, we took infrared and temperature programmed desorption data on benzene, toluene, phenol, and benzonitrile. And in the infrared, we made comparisons between the vibrational spectra. So we found that for all of the derivatives, the peaks they have in common, the 1500 peak and the 700 peak, the peaks actually split in the case of the derivatives. And so that is how we can tell toluene apart from benzene. And then in the case of phenol, we have a broad OH band, and in the case of benzonitrile, a CN band peak. And then for the TPD data, we found the desorption temperatures. So as we could see in this previous slide, both benzene and toluene desorb at lower temperatures than phenol and benzonitrile. So this tells us that in some cases in the interstellar medium, we might find, if we were to find these molecules in the ISM, we might find that benzene and toluene are in gas phase, while benzonitrile and phenol might still be in ice phase. And then from this, we combine all this data and we can find the binding energies, and we find that they are positively correlated with the desorption temperatures of each molecule. And then to kind of bring that all together and say, what does it mean? For the IR, when we look for spectra in space and take spectra of a molecule, we can then compare it to the spectra that we took in the lab and say, oh, this is exactly what we found for phenol. This must be phenol in space. for example, in the ISM. And additionally, we found that a molecule with a higher binding energy we expect to be in solid form closer into the star at a higher temperature in a protoplanetary disk than one with a lower binding energy. And finally, moving forward, we are going to take additional experiments for more precise error calculation. And additionally, we want to assign the spectral features for each vibrational mode. So I talked about in the beginning how sort of the movement of the hydrogen bonds correlated to a peak in the benzene spectra, but we want to find out what movement, what is specifically happening for the derivatives as well, and kind of characterize this and write this up. And then finally, we aim to calibrate the ice thickness to get the band strengths for toluene, phenol, and benzonitrile. Because as I said before, we were just using the band strength for benzene because that was all we had in the literature and didn't have time during this semester to calculate it yet. But in the future, the accurate band strengths for each individual molecule will be calculated, and thus we have a thorough understanding of these molecules in the interstellar medium. Thank you.
Thank you, Aurelia. We have time for some mic.
Our next presentation. I was curious about the results, the absorption temperature, and how that varied for the molecule. Is there any theory or simple physical interpretation as to why certain molecules are easier to sublimate versus?
I think most of it has to do with kind of the makeup of the molecule and the strength of the bonds. And that is kind of like what the binding energy talks about. So for benzene and toluene, it is just kind of, it takes less energy for these bonds to shift and change into ice phase than it does for the others.
So it's not like dipole or anything like that?
You know, honestly, I have not taken a...
It does differ by quite a bit, yeah.
Yes.
Yeah, Charles.
So you mentioned the substrate, the isoform one. So what is the substrate made out of? And is there any interference from the rest of the apparatus with
That I would have to get back to you on. I think I'll be writing about it in detail in my paper if you would like to check that out. But unfortunately, I don't know off the top of my head what it's made out of.
I'll send you a copy of the thesis, Charles. Or maybe Karen can tell you.
You know that it's glass, right? Because you have seen it.
Yeah.
So it's not grain.
It's just glass.
Well, a special kind of.
Special glass.
Yeah.
Charles?
Yeah, great talk. You might have said it and I missed it, but why does phenol and only phenol show these really broad emission bands?
Okay, so phenol has the broad OH band because it, like, how do I explain this? It's very good at, like, OH bonds are very easy to form, and so lots of them form, and it kind of broadens the peak because they don't just form specifically at a certain wavelength, like they do for the other molecules, but instead kind of over a broader amount because they're so formed so easily.
Can you make it quick?
Yes, simple question. Do these characteristic spectra you illustrate tend to disappear when the chemicals change from the gas state to the frozen state, to the crystalline state? Do you still see the richness of spectra in the crystalline state?
Yes. Yes, because, well, I think so. Yeah, yes, I would assume so because we're looking in the ice phase, and there's also been spectra taken of these molecules in gas phase that we looked at, and it's sort of the same peaks that we see from ice to gas. So I would assume that kind of in this in-between state, it would last and stay the same.
Okay. Thank you, Aurelia. Good job. Okay. So our next speaker is Kaylee Hostnet. She has been advised by Avi Loeb, and she's going to talk about a problem on high redshift galaxies, JWST, etc.
Hi, my name is Kaylee Houseconnect, and today I'll be presenting on the research that I've been working on for the past semester with Professor Avi Loeb. And we've been trying to identify galaxy merger candidates and developing cosmologically informed priors for the photometric redshifts of the earliest galaxies found with the James Webb Space Telescope. So since JWST has launched, the entire field of astronomy has been excited to see the images of data from its deepest fields, because besides being pretty, they can reveal the nature of galaxy formation and evolution in the early universe and aid in our understanding of cosmology. So admittedly, it's been a roller coaster since the early release program started putting out the data, because we repeatedly saw the redshift record being broken just to have some of this rolled back because of calibration issues. But finally, people are starting to become more confident in the redshift assignments of these galaxies. And in particular, we'll be analyzing 3 different fields from JWST. These are Sears, Glass, and SMAX 0723. And these are relatively small areas in terms of the square arc minutes, but they're analyzed to very deep redshifts. And so when we started this project, we had 2 kind of broad research questions that we were interested in. Number 1 was the tension that was emerging with lambda CDM. So this is a plot from a Boyle and Colchin paper from July, which the galaxies that he used have since been revised, but the point still stands. Some of the galaxies that are being identified by JWST are surprisingly massive for the redshifts that they exist at, including up to redshifts of 16. The other interesting question was about photometric redshift identification. So what JWST has made clear is that photometric redshift identification is a challenge, because here's a plot from another paper where people try to fit the redshifts of these galaxies and end up with these bimodal probability distributions, where lower redshift galaxies can masquerade as high redshift galaxies. And to achieve the science goals of JWST, we need to be very accurate in our redshift identifications. And so the analysis that I'll describe kind of explores both of these questions and ends up connecting the 2 of them. So the first analysis that I'll describe is what I'll call the nearest neighbor analysis. So because JWST is looking at very deep fields, the galaxies that it's identifying are actually very close together. And so what we do is we identify the nearest neighbor to each galaxy based on its RA, declination, and redshift. And on the bottom, you can see a histogram of the angular separation to the nearest galaxy. You can see that there's pretty small angular separations between the nearest galaxies in JWST. But these angular separations correspond to transverse proper distances at the redshifts of interest, which we can calculate using the angular diameter distance, and we adopt the cosmological parameters from the Planck 2018 collaboration. And then, in addition to fitting the redshifts of these galaxies, people also get measurements of the absolute UV magnitude. So from these absolute UV magnitudes, we try to infer a stellar mass from these galaxies using prescriptions for the UV stellar mass relation from the Baruzzi et al. Universe Machine paper. And then from the stellar masses, we can also infer the halo masses of these galaxies. And finally, our point in doing this is that we want to calculate what are the virial radii of these galaxies. And we do this with the equation on the plot. And the general trend when you calculate the virial radius is that for a fixed halo mass, the lower the redshift you're at, the greater the virial radius that you infer. And our goal in calculating the virial radius is that we can then compare the size of the virial radii with the distance between the 2 galaxies. And so for this analysis, we only used galaxies that fit a pretty strict redshift selection criteria. So because we're doing a nearest neighbor analysis, the more galaxies we include in the analysis, the more candidates we find. But essentially what I'm showing here is the proper separation of the galaxies divided by the sum of the virial radii to the nearest neighbors. And so what we see, I'll demonstrate it more clearly with this schematic, is that points that are above the horizontal line at 1 in these 2 samples that we analyze have halos that can be distinguished as being distinct for the 2 specks of light that we see. Whereas below this line, we would infer these galaxies to be occupying halos that overlap each other, meaning that they might actually just be distinct, like star-forming regions within the same galaxy. And we find 4 such candidates when we're just including the galaxies that satisfy the redshift selection criteria. And And why we might expect to see this with JWST is because in the early universe, the rate of galaxy mergers is expected to be much higher than it is now. What's also interesting to note is that 2 of these candidates hover around the 10% line. And we know that disks in galaxies tend to be about 10% of the virial radii. So what we might actually be seeing is not necessarily galaxy mergers, but distinct star-forming regions within these galaxies. And so we're starting to write up a paper, and we think that these candidates should be followed up on with ALMA or NGVLA, because number one, they can tell us more about star formation or galaxy mergers in the early universe. And also, another interesting facet of this analysis is that it might help reduce the tension with lambda CDM for these high mass galaxy candidates. Currently, people are looking at these 2 specks of light and identifying them as belonging to distinct galaxies with distinct halos, when really they might actually belong to one higher mass halo, but this could reduce the number density of halos that we're inferring at these redshifts. And so we wanted to stress test this analysis. So first, considering that at these high redshifts, there might be a more top-heavy IMF than we're assuming. So we do a very crude approximation of this by considering the number of ionizing photons per baryon. So this is about 4,000 for a salpeter IMF and up to 10 to the 5 for population 3 stars. So we essentially take the stellar masses that we infer and reduce them by a factor of 25, recalculate what their virial radii are, and we still find 2 candidate pairs which could belong to the same halo. The second way that we stress test this is by considering that maybe these galaxies actually exist at lower redshifts. And so this takes us to the redshift counterfactual analysis, which relates back to photometric redshift identification. So what we do is we take 2 redshift independent measures, which are the apparent magnitude of the galaxies in the UV band, and then also the angular separation between the 2 galaxies. And we imagine holding the apparent magnitude constant, but lowering the redshift of these galaxies. And then we calculate what would be the stellar mass, halo mass, virial radius, etc., that we would infer. So to be clear, the path for how we do this is we take the redshifts and the absolute UV magnitudes that are fit with JWST. From these, we infer an apparent UV magnitude, and we hold this constant as we lower the redshifts of the galaxies. The way we lower the redshift of the galaxy is by imagining like reducing the luminosity distance and adding an appropriate redshift K correction. And so we iteratively step down the redshift ladder. So here's like an example of the type of analysis we do, where we infer what the absolute UV magnitude would be for an apparent magnitude galaxy of whatever as we go to lower redshifts. And then the last 3 steps are the same as in the nearest neighbor analysis, where we then interpret a stellar mass, the halo mass, and a virial radius for these galaxies. And so what we find on the left, this shows the virial radius just for an example galaxy, but the trend holds for all the galaxies that we look at. We calculate the virial radius in kiloparsecs if we imagine this galaxy to be at a lower redshift. And we see that the virial radius in kiloparsecs increases. But then we scale this to be in terms of an angle using the angular diameter distance. And what we see is that the angle subtended by the virial radius increases as we move the galaxy to lower redshifts. And so what this means is that if these galaxies, we're finding that their halos overlap at higher redshifts, by moving them to lower redshifts, we actually get greater halo overlap for the galaxies. And this has implications even for the cases, which were the majority of cases, where there's no overlap between the halos, because it suggests that when we move to lower redshifts, there's tighter clustering of the halos. And so what we're working on is maybe developing like a prior based on lambda CDM of the redshifts of galaxies just based on their apparent magnitude. You might initially think that a lambda CDM prior would always favor lower redshift for high mass galaxies, but because the clustering becomes tighter as you move to lower redshifts, a prior would have to balance this. And priors are already used in fits of photometric redshifts, so it would be easy to like integrate this into the pipeline and see if this could maybe break some of the color degeneracies that we see in photometric redshift fits. So to conclude, I'll just recap the results. So we found 4 pairs of galaxy candidates that have overlapping halos We think follow-up observations with ALMA or NGVLA could be interesting. 2 pairs of the galaxy candidates are robust to assuming some approximation of a top-heavy IMF. We see that the overlap in the halo increases if candidates actually exist at lower redshifts, and we're working on developing a lambda CDM prior that could be useful in breaking some of the degeneracies that we see with the bimodal probability distributions. Thank you. And, oh, sorry. I forgot.
Finish up. Yeah.
Yeah, I forgot to acknowledge Avi, who couldn't be here today because he's giving a colloquium, and Professor Narayan for running a great class. And I'm excited to see everyone else's presentations. Thanks.
Thank you, Kelly. Okay. Time for questions.
Yeah.
Okay.
So you talked a bit about the redshifts and how certain or uncertain they are, but how uncertain are they? So I mean, if you have a pair of galaxies, how likely is it? I understood it to do the analysis where you're moving them both sort of away and towards you, but how likely or unlikely is it that they are actually more offset in Z than?
Yeah, so for this analysis, basically the way that we calculate we find the nearest neighbor means that they have to have overlaps in like their error bars for redshift, and then we just sort of lock them together, like assume that they're at the same redshift, which like based on, like, so one approach people take for like determining redshifts is called like cluster Z's, which basically is like you don't even look at the photometry, you just assume that because they're like situated very close together, like you can infer redshifts based on that. So we're making the assumption that if they're very close together and based on photometry, we infer the redshifts to like overlap in terms of the error, we like lock them together for this analysis.
Thank you.
So I was wondering, I think most of your analysis is based on the top-heavy IMF, is that right? Or 3?
The plots that I showed were based on not a top-heavy IMF, but then I just reran the analysis by like shrinking the masses by a factor of 25, which is just a real approximation, and see if the virial radii that we infer still overlap, and for 2 of the candidates they do.
Okay, but the top-heavy gives you more overlap? Which is the way it
Oh, the top-heavy gives less overlap.
gives less overlap?
Yeah.
Okay. So when you made it saltpeter, you got 2 more candidates.
Yes, exactly.
Okay, I see. Okay. Yeah, go ahead, Jacob.
Can 2 very close together galaxies pass by one another without merging, or is it, or if they're that close to one another, are they pretty much likely to merge?
I would think that like if they get very close together, like the friction, I guess, between them would make them merge. But maybe that is more on like a case-by-case basis.
Very good. Okay, thank you, Ken.
Thank you.
Okay, next we'll hear from Edgar Olay. He's been advised by Roseanne Di Stefano, and his talk will be on searching for candidate exoplanets in isolated neutron stars at X-ray wavelengths.
Slight intermission while you're setting up.
Oh, wait, no. Yeah. Caleb, you start with microphone. Oh, I see. Perfect. Okay. Perfect. So does that work? Yeah. Okay. So hi, my name is Edgar O'Neill, and I was working with Dr. Roseanne Di Stefano on searching for candidate exoplanets in isolated neutron stars at X-ray wavelengths. So I'm sure you are all familiar with the transit method, which has been one of the most, if not the most, influential tool for finding exoplanets. I think exoplanets.nasa.gov said that it's been used to find around 4,000 exoplanets, which is a majority of the exoplanets we have found so far. Interestingly enough, all of the exoplanets that we have found using this method reside within the Milky Way galaxy. And we know the conditions necessary for planetary formation, and we know that these conditions should exist in other galaxies. Therefore, there must be planets in other galaxies. The question is, what can we do to find them? It is far too difficult to observe individual stars in other galaxies just because of the density of the stars compared to like our compact field of view of the galaxy. So instead what we can do is we can look at the X-ray emitting objects, and we can look at the photons that we are receiving from those X-ray emitters, and we can see the dips in the photons and attribute those to different features. So essentially, a planet passing in front of an X-ray emitting region may produce a total or near total eclipse of X-rays, which is similar to the transit method. So my advisor, Dr. Roseanne, thought about this, and about a year ago, I think it was December of 2021, she thought about this and decided to look for these interesting dips and signals. And so her and this group published a paper on an external galaxy, M51, also known as the Whirlpool Galaxy, where they, the paper basically claims to find a candidate exoplanet through the X-ray dip. This paper sparked the beginning of something new, and since then her group has been searching for several interesting signals using these X-ray photons. And we can find things such as dips, but also things like flares, depending on the photons that we receive. My project for the semester was to search for these interesting signals in isolated neutron stars where a planet could theoretically reside. So there's different types of isolated neutron, or different types of neutron stars, such as young radio pulsars, millisecond radio pulsars, accreting neutron stars. But what I was focused on was the isolated neutron stars, which are powered by the thermal cooling and accreting from the interstellar medium, and they emit soft X-ray. So theoretically, we could find a planet or an interesting feature when looking at the light curves. So I looked at the quote-unquote the Magnificent Seven, which are 7 isolated neutron stars that were found in the Rosat All-Sky Survey in 1996. The reason I chose this was, first off, the data set perfectly fit the time frame of the 2 months. And even though the chances of finding an exoplanet we knew beforehand were low, it was still possible that we could find something interesting. So these are the Magnificent Seven. I was fortunate enough to work with 6 out of 7 of these. The 6 objects were using the Thesis instrument on the Chandra telescope. And since this project was focused on time variability, the Thesis instrument, which stands for Advanced CCD Imaging Spectrometer, these observations were the ones that were best suited for the project, which is why the last object on this list that has the star in it was not analyzed. So like I said, we used the Chandra telescope, and there were more than 700 light curves that I looked at with my eyes, and other people in the group looked at as well. Initially, to look at these light curves, the code that was given to me would only take in the coordinates and text files of one individual event. And so I had to manually input all of these coordinates and text files one at a time to look at one light curve at a time. After 550 of these light curves, a grad student that I worked with, Yeva, managed to automate the process so that we could put in the observation ID, and then it would give us all of the light curves. So that was after 550. I think it was like only 2 or 3 weeks ago that we managed to automate this process, thanks to Yeva. As you guys are, I'm sure, familiar, I also use DS9 imaging for the data of each observation. This is RBS 1556 in the blue circle, which I will be using data for RBS 1556 for the entire presentation. Most of the data is the same across all the isolated neutron stars, so I didn't want to show you a bunch of repetitive light curves and everything. So everything will be RBS 1556 except for one light curve, which I will get to later. But anyway, so DS9 imaging was very important for a couple of reasons. It was crucial for things like the proper motion and the position, because these were things that could tell us whether or not the isolated neutron star was moving or had some sort of deviation in its path, which could be attributed to a possible candidate orbiting the isolated neutron stars. It was also important for the region creation, which was very crucial for things that I will get to later, like variability and things like that. So this is an example of one of the light curves produced. Like I said, there was around 700 of them, and a majority of them looked like this. So there's 3 different plots here. The upper left is a light curve with a bin size of 1,000 seconds, so 1 kilosecond. We could choose the bin size, but we always started with 1,000. But obviously that depended on the amount of photons that were coming in and things like that. The upper right is a running average over 3 bins. This was really useful because sometimes we just wanted to see whether or not there was a dip immediately, which is why that was useful. It was really nice to see the immediate effects from the code. And then the bottom was just a cumulative photon counts versus time graph, where it's basically just like over this amount of time, these are the photons that we received. This was also nice to look at because occasionally you would get 1 or 2 graphs that had a slight dip or a large variation, and so it was helpful to look directly at the cumulative light curves. We also had hardness ratio plots. This plot here in the corner is the only one that is not RBS 1556, but I included it because it is different than this one, which is also a majority of what we got. So the blue is the error, and the black line that's the hardness ratio, that plot that we got. So essentially the hardness ratio compares the number of counts observed in different passbands. It's equivalent to the photometric color index and is calculated as a normalized difference of the exposure-corrected counts in different energy bands, being high energy and low energy. It essentially compares the number of counts observed in different passbands, and then we can use this to distinguish whether or not the photons are hard or soft. So like I said, the top graph is RBS 1556, and this one I think is RxJ 080623. Then I started to look at the short timescale variability. So this is a light curve produced through CHOW, which is the Chandra Interactive Analysis of Observations tool. And so this light curve has no variability, and it properly matches the variability index that was given from the algorithm, which I will show in a moment. And the errors shown here, the red bars, are likely outliers. But CHOW uses the GL algorithm, which stands for Gregory-Laredo. I will explain that a little more in a moment. But essentially, what it does is it will produce a light curve that is generated. The light curve that was just presented for that observation for RBS 1556 consists of the binnings weighed by their odds ratio and represents the most optimal resolution for that curve. So the GL algorithm will give you the most optimal resolution for that observation. And the way it works is it goes through n events and bins them in m bins. Oops. And then it provides a ratio related to the probability of an observed distribution occurring by chance. And the odds are summed over all values of m to determine the odds that the source is time variable. So essentially, we get 3 things from this algorithm at the bottom here. The red circle is the variability index, which we can match up to this table that's presented by CHOW. And as we can see here for RBS 1556, the observation that I used was definitely not variable. So for planetary transits, null results are still results. after going through all of the light curves for 6 different isolated neutron stars, there were no signs of a significant dip in X-ray photons that suggested that there was a candidate planet orbiting these objects, which we assumed from the beginning. We kind of thought that that would happen. A majority of the light curves had unchanging cumulative photon plots. The hardness ratio plots correctly show that the photons were soft as expected, and the GL algorithm showed that there was no real variability that was worth attributing to a planetary candidate. What we did learn, though, interesting information anyway, was that although we didn't manage to find an exoplanet, we still found something interesting. It was the consistency of the isolated neutron stars. So these are 6 graphs, each of them for a different isolated neutron star, all of them looking mostly the same, where we have no real dips and are pretty consistent with the photons coming in. And then I wanted to give a special thanks to Dr. DiStefano, my classmates, but also Yeva and Caleb, who I'm not sure if he is here today, but without them too, I couldn't have done this project. They were by my side the entire semester, but thank you.
Thank you, Edgar. We have time for a few questions. John?
It went by pretty quickly, but it looked as though on that last plot you had, the last one on the right looks like there's some curvature to it. No, the bottom one. Well, okay, either one of them.
Yeah, so for the Python program that we made, this kind of goes back to the binning a little bit. Sometimes the edges they weren't quote unquote real because it depends on the amount of photons that you're receiving. So for some of these, the edges themselves are negligible, and what is important is, I guess, the center of the graph. But again, that depends on things like the bin size and things like that. For these plots, I included everything, including the edges.
Yeah, I actually wanted to ask pretty much the same question. I would have thought these are these isolated neutron stars doing nothing, that their light curve would be flat.
Mm-hmm.
None of these guys looks flat to me.
Mm-hmm.
Are those all just part of the noise, or is there some real variation? I mean, the one that John pointed out is very obvious.
Mm-hmm.
That's not flat. But even the others, I'm seeing some variations.
So most of it is noise. It also depends because the Chandra telescope basically just receives individual photons. So things that need to be taken into account are, for example, the dithering of the telescope, which matches up exactly. So let's say the dithering is the movement of the telescope. If the telescope moves slightly and we receive a photon from the isolated neutron star at one place, and then it moves slightly again and we receive it at another place, that would change where we're getting the photons. So each of these individual plots are the isolated neutron star, but there's also light curves that I got for the background and right next, close to the neutron star and things like that. So, yeah.
Right, Charles?
Just out of curiosity, the data were all archival data, correct?
Sorry, I couldn't hear you.
The data you're using were in the Chandra archive?
Yes, yes.
So were those taken for the purpose of studying these objects, or were these incidentally in the image frames?
I think these were for these objects. They're pretty old. I think the newest one out of all the observations from the archive was 2006 or 8. But I believe that they were for these objects. Most of whenever I went into DS9, I think I can show you. That bright spot up there is actually a galaxy. I went back and checked the coordinates and everything, but most of them were just the isolated neutron star that were received from the telescope, from the observation.
I guess the fact that it's in the middle means that was the target.
Yeah.
Very suggestive, yeah.
Okay. There are no other questions. Thank you, Edgar. Okay, next we'll hear from Chija Zhao. She's been advised by Karen Oberg and Alexia Simon, and she's going to talk about competitive entrapment of hypervolatiles in water ice.
All right, hello everyone. My name is Chija, and I worked on an astrochemistry project this semester in in Professor Oberg's lab, and I was investigating competitive entrapment of hypervolatiles in interstellar ices. I'll start just by introducing some of the astrophysical context for my project. So we're specifically interested in planetary formation in protoplanetary disks. So we're interested in, first of all, the chemical abundances of different species at different parts of the disk, since that impacts what chemicals are available to form planets with. But we're especially interested in the phase of these chemicals within the disk, since if the chemical is in a solid phase, then it's likely to get accreted into the core of a planet, while if it's in a gaseous phase, then it would be part of the atmosphere of the planet. So kind of a basic model we use to determine whether or not an element will be solid or gaseous is the snowline model. So in a basic model of the protoplanetary disk, the temperature decreases as you get further away from the star. So based on this temperature of the average temperature of the disk at a certain radii, and matching it up with the sublimation temperature of an element, we can determine a snowline, which is, for example, with nitrogen. So inside the snowline, we would expect nitrogen to be in the gas phase, and outside of it, we would expect it to be in the solid phase. But there are obviously there's some variation between the different species and where their snowlines are. So some volatile elements, like water, so it appears pretty close to the star in this diagram, but obviously water is a little bit more volatile than refractory elements like rock. But water has a pretty close snowline, but we're specifically interested in hypervolatiles. So while there's some volatile elements that have snowlines closer to the star, there are hypervolatile elements that have snowlines very far away from the star in the outer outskirts of the protoplanetary disk, like methane, CO, and nitrogen. And we're interested in these elements because normally just from this very basic model, we wouldn't expect to see those hypervolatile elements close to the star in the solid state. But we've seen some observations of comets and solar system planets that seem to indicate that they were available in a solid state because they were accreted into the core of the planet or the comet close to the star. So one of the leading mechanisms for which we can explain how this can occur is entrapment. So entrapment can be defined as a mechanism by which hypervolatiles are retained within a less volatile ice matrix beyond their typical sublimation temperature. Just to more concretely show this, imagine there's this ice particle that's like a water ice particle, and then these nitrogen molecules, which are hypervolatiles, could get trapped by getting stuck basically within the ice matrix of the water molecule. So they get stuck between the gaps between the molecules. So to show this inside the protoplanetary disk, you can imagine that this sort of ice mixture particle starts out outside of the nitrogen snowline, and then it can move in pretty close to the star inside the nitrogen snowline, but still stay solid because it's mostly a water ice matrix. And then we would expect it to sublimate as we would expect with just pure water ice, since, again, it's a mostly water ice matrix with a little bit of hypervolatile entrapped in it. But as you can see from there, the nitrogen molecules that are entrapped inside this water ice matrix are still considered to be in their solid state, even within the snowline. So then if this ice particle is accreted to the planet, then the nitrogen was accreted as a solid instead of a gas, as we would have expected from a basic snowline model. And there have been some previous laboratory experiments to test the entrapment efficiency, basically what percentage of an available hypervolatile can actually get entrapped inside the water ice. And for a lack of a better word, there's some tension between some of the previous findings. So in 2007, Barnum et al. Did a qualitative experiment with 4 components, so a water ice base, and then 3 hypervolatiles, CO, nitrogen, and argon. And they found that CO and argon were much better entrapped than nitrogen by about an order of magnitude difference. However, there's some more recent quantitative analyses with just 2 component mixtures, so water and then 1 hypervolatile. And Simon et al. Found that the entrapment efficiency was about the same, hovering between 40 and 60% among all of the hypervolatiles. So one of the main theories that we propose to explain this discrepancy is competitive entrapment. So maybe some hypervolatiles, when in the presence of other hypervolatiles, are better entrapped than others. So then the discrepancies don't show up in the 2-component mixtures since it's just 1 hypervolatile in the presence of water. But then when they're in the presence of each other, for example, in that 4-component mixture, maybe CO and argon are just somehow more easily entrapped than nitrogen, and thus kind of outcompete nitrogen for those entrapment spots. So my experiment attempts to do a quantitative analysis of this of competitive entrapment to see if it exists, and if so, to quantify the differences. So these are the 3 types of experiments that I did this semester. They all have water ice base, and then CO as the first hypervolatile, since CO is much more abundant than all of the other hypervolatiles in the ISM. And then we're testing competition between CO and then nitrogen, CO and argon, and CO and methane. In addition, we do want to start with 3 components instead of 4, like the one that Barnum did, because we want to try to isolate the degree of competition between the specific chemical species. I also point out that we try to keep the aim ratio, so like the ratio between the different chemical species, as well as the thickness of the ice, the same for all of these experiments to try to isolate the differences in entrapment to just the differences in the species, instead of like maybe if there's different ratios, there are also different entrapment efficiencies. And to go over a little bit about the experimental setup, how I was able to determine these entrapment efficiencies, I use the same instrument as Aurelia, as you saw earlier. It's called Space Kitten. And you can see that there's the main experimental chamber in the middle, covered by tinfoil. And we're able to mimic ISM or disk conditions in this chamber through the cryocooler. So it cools down the sample inside the chamber to about like 13 to 14 Kelvin. And then we also have a vacuum pump. You can't see in the pictures, right underneath the chamber, and it can keep the pressures extremely low to like 10 to negative 9 torr. And then we also have this gas dozer on the side. So basically, I think you saw in Aurelia's presentation, there's like a whole complicated gas mixing contraption, and then this dozer kind of pump all that gas into the chamber. Then I could show a little inset. So this is like a picture inside the chamber. So you can see that there's that sample holder with the little like glass window, and the dozer, you can just see it on the side, and that's how we deposit the gas onto the sample holder, and it forms the ice on that. And to also quickly go over the instruments that I used. So there was 2 instruments. There's the IR spectrometer. So this was used to find the ice thickness and the ice mixing ratios, again, the things that I wanted to keep constant across all the experiments. So how that works was that an IR ray was shown through the sample holder, and then we could get that from the IR detector, which forms the IR spectra. And then the important one is the mass spectrometer. So that's labeled as the QMS detector on the bottom in red. So that basically can measure how much of each molecule is like getting pumped out in gaseous form as we're running experiment. So this is also a good time, I guess, to describe like the procedure of my experiment. So once we did cool down the chamber to about 13 to 14 Kelvin, we deposited the gas onto the sample holder to form the ice, and then we did temperature programmed desorption, so TPD, again, same thing that Aurelia described. And during this TPD, we heated up the chamber at a rate about like 1 Kelvin per minute until the ice fully desorbs. So the QMS detector can kind of detect as these molecules are desorbing as we heat up the chamber. And just to visualize that data that we get, I have a plot from one of my experiments with water, CO, and methane. As you can see, there's a temperature on the x-axis, so the temperature of the sample, and then on the y-axis is the QMS count. The QMS count is basically proportional to the number of molecules that the QMS detector detects at a certain temperature. I've plotted the sublimation temperatures of each species in these vertical dotted lines. So the two on the left at the lower temperatures are the sublimation temperatures of the hypervolatiles, which as expected are pretty low. And then the one in orange here closer to me is the sublimation temperature of water. And you can see that there are like kind of two groups of peaks on this plot. So the peaks that are close to the sublimation temperature of the hypervolatiles are just the regular, again, the hypervolatiles sublimating at the temperature we would expect them to if they were not entrapped. And then the ones on the right, which are you can see there are some hypervolatiles sublimating at the same temperature as water, and that's what we would expect to see if these hypervolatiles were entrapped in the water ice. And I think this next plot explains a little bit about how I calculated the entrapment efficiency. So again, as I said, the left peak kind of represents the hypervolatiles that were not entrapped, and then the right one represents the hypervolatiles that were entrapped in the ice. And then we can integrate the area underneath these peaks to determine like the total number of molecules that were entrapped versus not unentrapped. And then we can calculate the entrapment efficiency by dividing the total entrapped peak area over the total integrated area. So essentially that's just all of the entrapped molecules divided by the total number of molecules that are in the chamber. And here is the TPDs for all of my experiments. So I did 3 with CO and nitrogen, 2 with CO and argon, and 1 with CO and methane. As you can see, entrapment does occur in every single experiment since there's a peak at the water sublimation temperature for each of them in the hypervolatiles. And you can sort of already estimate like the relative entrapment efficiencies just by looking at the approximate area under the peaks. Though I think this is better shown in this bar graph. So for all the different experiments, I have like the comparisons between the entrapment efficiencies, comparing CO and N2. So nitrogen seems to be slightly less well entrapped than CO. Argon, maybe a little bit. It's on the borderline of being significant with being less well entrapped than CO. And then methane appears to be much better entrapped than CO. Though I just wanted to point out that these differences seem to be only on the order of like 10 to 15%. Like these lines kind of show the total range of different entrapment efficiencies that we detected through our experiments. And it ranges from like 40 to 70%. So this is still pretty close to the entrapment efficiencies that Simon et al. Found in the binary component mixtures. Again, her entrapment efficiencies range from like about 40 to 60%. And it doesn't seem to show the same, like the order of magnitude difference that bar none reported in their experiment. So just to kind of summarize with some discussion, here's the approximate order from least to best entrapped from my experiment. So like nitrogen, then argon, CO, and then methane. And we're interested to try to explain like why we see these differences. We think that maybe the binding energy, so maybe there's some weak interactions between these hypervolatiles and water that can better bind some molecules than compared to others. And also molecule size might play a role in how well or how easily these molecules can fit into the gaps between these water molecules. And some future experiments we want to run are 3-component experiments without CO. So between like nitrogen, argon, and see if like this order can still be preserved in those experiments. And also we might run a 4-component experiment with all of the hypervolatiles to try to mimic like Barnard's experiments. Maybe we'll see something different. And then I just want to summarize with like 3 main takeaways. So entrapment is the mechanism by which a hypervolatile can be retained in a less volatile ice. And we detected it in every single experiment. We know that entrapment can shape the composition of planets and planetesimals in different areas of the protoplanetary disk. And again, maybe if there's competitive entrapment, that can adjust our models for like which elements we expect to be like more present in their solid form in different parts of the disk. And finally, my results seem to show that some degree, a small but significant degree of competitive entrapment occurs on the order of about 10 to 15%. All right. Thank you guys for your attention. I'll take questions.
Thank you, Teja. Okay, we have time for questions.
Sure. Maybe you could speak a little more about the rate at which the ice is formed, and if you played with that variable at all, and you think it might have any impact on the relative entrapment ratios?
Yeah. So the way that we form ice is so we mix we have all our elements in like the gaseous form, and we mix those gases together at the correct ratio outside of the chamber, and then we deposit the gases into the chamber, and since it's very cold, they'll just form onto the substrate. I do know that there's some other experiments that first form the water ice, and then they deposited gas onto the ice, and I think they might have some different results though. I think the results that we're comparing to, Simon et al. And Barnum, it was making the gas mixture outside of the chamber and then depositing once it's mixed into the chamber. Yeah.
Charles, do you have a question?
I'm trying to formulate it clearly, but I'm struggling a little bit. So these are these dilute entrapments in the sense that is there a small amount of nitrogen in a lot of water, or are the number of nitrogen molecules comparable to the number of water molecules?
Oh yeah, that's a really good point. I probably should have emphasized that. Yes, it's very dilute. So we have a 10 to 1 ratio between the water and and the hypervolatiles. So I think that in Simon et al.'s paper, they did test a 3 to 1 ratio between water and hypervolatile, and it has some I think it's less well entrapped. So we tried to use not sure, more astrophysically accurate ratios.
Thank you.
So you started off by saying that there was some tension between the Barnum experiment and the Simon experiment. Then you have done this new work. So what is, are you favoring one over the other, or you're just sitting in the middle and where are we?
So I think that since Barnum's experiment is also very just qualitative, they only ran one experiment, we can't really control our compare our exact entrapment efficiencies. But I think that from our experiments, we can kind of see that we don't see that an order of magnitude difference in the different entrapment efficiencies, which is what Barnum's paper implies. So it seems like we are matching a little bit better with Simon et al. But
so in your conclusions, should you have said Barnum is wrong or something like that?
I didn't want to be too controversial.
Yeah. We're worried that he might be the referee of the paper, so.
So you have to be careful. Yeah, okay. Good, yeah. You're teaching them well. Okay, very good. Thank you, Teja.
Right, thank you.
Okay, next we'll hear from Gabriel Maxinen. He's working with Roger Fu in the Earth and Planetary Science Department. He's going to talk to us about what the Murchison meteorite reveals about magnetic fields in the solar system's protoplanetary disk formation. Good.
Okay. Yeah, my name is Gabriel, and I'll be presenting on what the Murchison meteorite reveals about our solar system's protoplanetary disk formation, with my advisor being Roger Fu in the EPS department. So first, for some background, we know that gravity caused a spinning molecular cloud to collapse, and we know that more spinning and more collapse led to our protoplanetary disk. And within the protoplanetary disk, we know that mass is accreting inwards towards a developing star, which means angular momentum must have been transferred outwards. And this transfer of angular momentum, the mechanism driving it is poorly understood, but it is suggested that magnetic fields played a major role in this. And in order to study this angular momentum transfer mechanism, we're using the Murchison meteorite, which is of interest because we know that the Murchison meteorite formed during active protoplanetary disk formation. And on the left, you can just see the sample that we have in our lab of the Murchison meteorite. And then on the right is a thin slice that we have, just as an example. And so within the Murchison meteorite, what we're focusing on is dusty olivine. So first, for some context, the Murchison meteorite is a chondrite, and chondrites contain chondrules. And then within the Murchison meteorite, there's these chondrules that contain dusty olivine. And olivine is a mineral in a rock. And what makes it dusty is that it has high magnesium and these iron inclusions that are reliable records of early solar system magnetism. And then in this figure, you can see just like the spherical shape is the chondrule, and then within the dashed lines is the dusty olivine that we're looking at. And in order to study this, we use the quantum diamond microscope, abbreviated QDM. And what's special about this is that in comparison to other magnetic microscopes, this provides us really high resolution, or really good resolution of 1 micron. And some useful outputs that we get from the QDM are the morphology of magnetic dipoles present in our sample, as well as a quantification of the magnetic moment of these dipoles. And then I'll just talk about the methods that we used for this project. So first, we have on the left our entire meteorite sample, and then we used a wire saw to cut 200 to 300 micron slices, and then we placed these on a quartz disk. And then from here, we used a microscope to analyze the like each of the slices. And like within this graphic, the pale green blob in the center over here is our dusty olivine, just for some context on the next few graphics. Yeah, so we looked through the entire slice to pick out all of these dusty olivines. And here you can just see an example of what they look like under the microscope under different types of magnification. And so what we wanted to do is to make sure to isolate the dusty olivine so as to get signal just from the dusty olivine chondrule and none of the matrix and the other chondrules. So what we did was we drilled out everything that wasn't the dusty olivine chondrule and then placed it on a glass slide with a thin film over it to protect it. And then after this, we were able to put each of the dusty olivine chondrules on the QDM. And then from here, we get this output. On the top is just a graphic of it, but down here is what a real output looks like, showing like the best fit dipole of this dusty olivine chondrule. And then red here means like out of the page, blue into the page to tell us the direction of the dipole. Okay, and then a big part of this project was alternating field demagnetization. So just for some background on this, when we're measuring the magnetism of a rock, we're trying to measure the natural remnant magnetization. And what this means is that it's the magnetization of a rock without any lab treatment or otherwise any induced magnetization. And the NRM, or natural remnant magnetization, comes in two different forms. It's primary and secondary. And primary comes from the time during rock formation, and secondary comes from any time after that. And because we're interested in active protoplanetary disk formation, we're interested only in primary NRM. So we need some way of getting rid of this secondary NRM. And the way we do this is by applying an alternating field demagnetization. And how this works is we apply this alternating sinusoidal linearly decreasing field in magnitude with time. And then any grains that are magnetized below this applied field will have alternating magnetizations so as to cancel out the net effect of all of these weaker grains. And we know that these weaker grains correspond to secondary NRM. So then we successfully isolate the primary NRM. And this is just a graphic showing what we do is we place the sample on a demagnetizer, and then after we have demagnetized it with a certain field, we run it on the QDM, and then repeat this entire process, but each time incrementing the alternating field strength by 25 Gauss. Okay, and then after we've run the alternating field sequence, we have exactly how magnetized our dusty olivine chondrule is. However, we still have a problem, and it's that just from how magnetic our chondrule is, we can't really know the temperature that the grains were heated at or the strength of the magnetic field that the dusty olivine chondrule was in, because we don't know how easily a chondrule is able to acquire a magnetic field. So our workaround around this is to apply an anhysteretic remanence to simulate thermoremanence. And then thermoremanence is just the magnetic remanence acquired from a magnetic field during rock cooling. And the way we did this is we put the sample in our 2G magnetometer and then apply that anhysteretic remanence. And just a view of our results. So this is for dusty olivine chondrule 1.10, which means from slice 1, it's dusty olivine 10. This is an example. As you can see, what I mentioned before was we apply alternating fields increasing in strength by 25 Gauss. And as you can see, the morphology kind of stays the same for the most part, and it's decreasing in strength as you go up. However, after a certain point, like here at 900 Gauss, you see that the morphology starts to change, which means that we have demagnetized this significantly so as to remove a lot of that secondary NRM. And this graph is really complicated, so first I'll focus on kind of explaining this. So this is, any point on this graph is how magnetic this chondrule is, or how far from the origin it corresponds to how strongly it is magnetized. And so if we just focus on the top graph, okay, before that, this is like a 3D graph because like it's a vector, the magnetic moment. So it's put into a 2D graph by way of the two graphs with the different either z-axis or north-south axis. But if you just focus on the top one, 0 labeled there would be without applying any alternating field, and as you go up, it's applying more and more. And from steps 5 to 8, you can kind of see this linear decrease towards the origin, which indicates to us that we have removed the secondary NRM, and we're simply decreasing in magnitude of that primary NRM. And this is kind of like the most significant result that we have so far. And it suggests that our dusty olivine chondrules were magnetized with multiple components. And what's also significant about this that I talked previously is that within this project we're using very fine resolution. And we know that this magnetization is sourced from the dusty olivine chondrule itself and not from the matrix or any other chondrules around it. And just as some other examples, so this is for a different dusty olivine chondrule. You can see at the top, this is what we had at an alternating field of 350 Gauss. We had this dipole that was very well fit, but then as soon as we hit the 400 Gauss mark, you can see this, the dipolarity was just really hard to see and we couldn't really make a fit of it, which told us that we had demagnetized the chondrule completely. And this is an example of us running the anhysteretic remanence on this dusty olivine chondrule. And this is what we have so far, but we plan on continuing this sequence through the entire this previously, it went up to 400 Gauss, and we're currently at 50 Gauss, but we plan on running it all the way to the 400 Gauss, so that from here, we can have a ratio of the magnetization from the ARM to the NRM, and then from this, we have a correction factor that allows us to get the intensity of the magnetic field in the protoplanetary disk. And this is just an update on a different dusty olivine chondrule. It's still going strong at 250 Gauss, and we'll keep it going, increasing at 25 Gauss. And then I also want to talk about some next steps for this project. Obviously, we would want to get as many dusty olivine chondrules as possible to get just a stronger result. So we would want to continue slicing and then identify even more dusty olivine chondrules and isolating them for analysis, as well as running all of them through their alternating field sequence, and then again applying a thermal demagnetization or simulating this thermal demagnetization to get an estimate of the field intensity of the disk. And then after we get this, we can compare our results for these different chondrules to get a more representative result, and then compare these results with bulk estimates of the entire Murchison meteorite that have already been made, which would tell us whether the dusty olivine chondrules formed locally or outside in another environment. And finally, I would like to acknowledge my PI, Roger Fu, as well as a PhD student, Sarah Steele, for helping me, and Professor Narayan for this amazing class. Yes.
Okay, so we have some time for a few questions. It's not a raised hand, is it? Just a thumbs up. Okay. Yeah, Charles.
So the original magnetic field that got this little piece of material started, is the hypothesis that it's the magnetization of the protoplanetary disk that produces the original magnetic field?
Yes, that it produces the primary NRM number.
And is there direct observational evidence for that magnetic field in the spectroscopy of the disks?
I'm not sure, actually.
It's not unreasonable because we see magnetic fields in lots of different places.
There are some experts here.
They're very difficult.
There are limits.
Yeah.
There are limits. Okay.
Thank you.
Right. So I had a question. So you have this sample which contains both primary and secondary NRM field, right?
Mm-hmm.
And then you send it through your machine, which does this alternating trick, and you are steadily increasing the amplitude of this alternating signal. That's the experiment.
Yes.
And then things are changing, but I was expecting in the results that you'll say, up to this point, I have not touched the primary NRM, but I'm getting rid of secondary NRM. Then from this point on, I have only primary NRM, and then finally it also gets eliminated.
Yes.
Maybe it is there in that funny looking graph you showed us, or maybe in the images. I missed the point. Where exactly are these things happening?
Yeah, I think I have been talking about this graph for so long with my PI and the PhD student, but apparently this is one of the better looking graphs when you do this type of analysis, because you can actually see from 5 to 8 kind of a linear decrease, but there's just so much noise that from 0 to 4 is where we're eliminating that secondary.
Secondary is being eliminated.
Yes, and then at 5 is where we think we may have already eliminated the secondary NRM, which is why we have just that linear decrease.
Okay. And then the linear decrease is because you're slowly killing the primary.
Yes.
And so 0.5 is where you get the intrinsic primary magnetic field strength.
Yes.
And that is what one should go and compare with what the astronomers measure.
Well, once we apply the thermo, the ARM,
okay.
then we get the correction factor to then get the.
Thank you, yeah, I
Yes.
think,
Mhm.
that's very nice, okay. It's good to see a field with graphs that are worse than I thought.
Yeah.
But, but once you explain it, it's all making a lot of sense, okay. Great, John.
When you talked about drilling out the region around the chondrule,
Mhm.
you showed a typical, DeWalt drill there. Is there a special procedure to avoid getting temperatures too high or vibration too much that would destroy the magnetization?
I'm not sure about the. Okay, this drill is not very accurate. Yeah, it's much smaller than this. But I do know that it's a clean lab, so everything we make sure to nothing's magnetically contaminating the sample. So I know that for sure. About the vibration and maybe thermal aspect, I hadn't considered that, but maybe that's a point worth bringing up to my PI.
Okay. Okay, thank you. So we will have a short break now. You can come back around 3:45. I think there are some refreshments in the back. Ooh, what? Yeah, something to keep you all going so that you will stay on. We have 4 more talks after the break. Fantastic, all of you. Is that too dark? This is too bright. Okay, that should do the job. I think. Screen is okay?
Yep.
Good.
Thank you.
You have your microphone on?
Yes, everything's on.
Okay, everyone. Thank you for those of you who have stayed on. We have 4 more excellent talks. So now we'll hear from Michelle Lynn, who is being advised by Dave Latham and Alison Biarella. She's going to talk about TOI 2473 and tell us about brown dwarfs and other good stuff. Yeah.
Okay. Hi everyone, my name is Michelle Lynn, and for my research project, I'm investigating TOI 2473, where I will be characterizing a transiting brown dwarf as well as a nearby eclipsing binary. My advisors for this project, Dr. Dave Latham and Alison Biarella. So for those who don't know, TESS, which stands for Transiting Exoplanet Survey Satellite, is a satellite that surveys the entire sky to detect transiting planets. So here is a lovely image captured by TESS. However, because TESS has to cover such large portions of the sky, it has very large pixels. Specifically, its pixels scale 21 arcseconds. And what this means is that as a result, it is not uncommon for many stars to be located in the same pixel. So here is an example of a TESS image with its pixels, and you can see that on this pixel right here, there are 2 target stars located within the same pixel. And the reason why we care about this is when we're working with transits. So a transit is basically when a smaller body passes between an observer and a larger body. And when observing transits, we can create transit light curves such as this one that essentially just observes the change in brightness of a target star. So for example, you can imagine that when a planet passes in front of a star, it will change the brightness of the star, which can then be observed in the transit light curve. Notice how for this transit light curve, there are kind of 2 different dips. And this is a result because if we have a system that says, like, let's say has multiple planets, and these planets are of like different sizes, then whenever each one of these planets transits in front of the star, it will change the brightness of the stars differently, which then results in these different dips. And so the y-axis usually, there's no y-axis here, but usually it represents the brightness of the target star, and the x-axis represents the time in which the transit occurs. So in most cases, when we see these multiple different dips, they're usually pretty accurate and representative of a multi-planetary system. However, there are cases when we can have a false positive. And what this means is that one of the transit dips that we see are in fact not actually coming from a transiting companion. Now this happens because, again, going back to the large pixel sizes of TESS, let's say if we wanted to observe the transit light curves of this star, in doing so, because there's another nearby star located within that same pixel, then the light from that nearby star also blends in with the light of the target star that we're observing. And as a result, this blending and contamination of the light may then result in a dip that can be mistaken as a planet, although this is relatively rare. However, in the cases that this happens, there are methods that we can utilize to distinguish and identify these false positives, which is what I will be doing in my research. So first, we are using the wide-angle ground-based photometric surveys. Specifically for my research, I will be using Kepler-Cam on a 1.2-meter telescope. And Kepler-Cam has high-resolution seeing-limited photometry. And what this means is that it has better spatial resolution, which results in a cleaner separation between the light of 2 stars, so we don't have to worry about any light contaminations from 2 nearby stars. Now, this is because TESS has much smaller pixels this is because Kepler-Cam has much smaller pixels compared to TESS. So Kepler-Cam has pixels of scales 0.67 arcseconds, while again, TESS has pixels of scales 21 arcseconds. So what this means is that if we given an image of Kepler-Cam and we look at its pixels, we can see that each pixel contains at most only 1 star, which means that we don't have to worry about any light contamination. The next instrument we're using is also TRACE on a 1.5 meter telescope. So TRACE is great for getting spectra to derive radial velocities from a system. And from those radial velocities, we can obtain an orbital solution of the system. Now, these orbital solutions are useful because if we're given a transit light curve and we see that they contain dips that may be representative of a multi-planetary system, this should also be reflected in the orbital solutions that we produce from TRACE. So in other words, we can kind of use TRACE as a way to confirm whether or not these transit light curves actually contain multiple transiting companions. So for my research project, I am investigating TOI 2473, which was a test object of interest. It was specifically originally identified to contain 2 transiting planets with periods of 1.2 days, which is represented by the red arrow, and period of 6.5 days, which is represented by the green arrow. So from the start, this looks like a star that is hosting 2 planets. However, we followed up with observations using TRACE to obtain the radial velocity of the TOI 2473 systems, and from the radial velocities produced a spectroscopic orbit on the right. So from this orbital solution, we can see that we found a period that matched only with the 1.2 day transit that was originally found in the test light curve, with no sign of the 6.5 day transit anywhere. And so what this means is that we were unable to detect the presence of the 6.5 day transit in the orbital solution. So this is possibly a false positive in the TOI 2473 system, in the case that this system only has 1 transiting companion with a period of 1.2 days. I also solved for the minimum mass of the transiting companion using that equation, and I found the mass of the transiting companion to be about 42 Jupiter masses, which is indicative of a brown dwarf companion. Sign I there represents the orbital inclination of the system, and here we assumed an orbital inclination of 90 degrees, and M1 is the primary star, or in this case, the host star of the TOI 2473 system. So based on that orbital solution, we now know that TOI 2473 does not actually host 2 transiting companions, but rather 1 with a period of 1.2 days, which then raises the question of what could be causing that 6.5 day transit. So a possible explanation then is that that 6.5 day transit was a result of light contamination by a nearby stellar system, which further raises the question of where that source could be, or more specifically, which stellar system could be causing this contamination. And we identified the source to be a nearby eclipsing binary located 42 arcseconds away from TOI 2473. Specifically, the light from this nearby eclipsing binary could be contaminating the light of the TOI 2473 system, which is what is causing us to see that 6.5 transit dip. And the way we identified this to be a source was again by using TRACE to obtain radial velocity observations of the eclipsing binary to produce an orbital solution shown here. And from the orbital solution, we were able to find that the eclipsing binary had a period of about 6.5 days, which we can see is consistent with the period found in the original test light curves. So what this means is that the period from the orbital solution matched up with the photometric period from the original test light curves, and as a result, we have then confirmed that the 6.5 day transit was indeed a false positive and was a result of contamination from this nearby eclipsing binary into the TOI 2473 system. Similar to the brown dwarf, I also saw for the minimum mass of the transiting companion, and I found that it was about 216 Jupiter masses, which you can see is much too large to be a planet or a brown dwarf and has to be a star. So kind of further confirming this is indeed an eclipsing binary, specifically that has a late M dwarf companion. So from the orbital solutions, because we were able to confirm from those that TOI 2473 actually only contains 1 transiting companion with periods of 1.2 days, and that the 6.5 transiting companion was a result of a false positive from a nearby eclipsing binary, we now want to better characterize the 2 transiting companions. Specifically, we want to better characterize the nearby eclipsing binary as well as TOI 2473 with its brown dwarf companion. And the first stage of doing so was creating non-contaminated high-quality light curves by using Kepler-Chem images. And again, the reason why these are kind of non-contaminated is because Kepler-Chem has much smaller pixels compared to TESS, so we don't have to worry about any of the target stars being located within the same pixel, and we don't have to worry about any light contaminating or blending with one another. To create these light curves, I use AstroImageJ, or AIJ, which is a photometric software analysis tool. And the way that AIJ works is that we first start off with a series of images around our target system before, during, and after the predicted times of the transit. We then calibrate our images using bias and flat field frame, which then results in a series of calibrated images such as this one. We then want to locate where our target system is. In this case, they were located in the upper left corner. And zooming into that region, all these green points represent stars that were imported from Gaia that were located within 2.5 arc minutes away from TOI 2473, which allowed us to locate where that system was. Now, if we can imagine kind of placing a test pixel on top of this, we would see that there may be stars that are fit within the same pixel. However, the really nice thing about Kepler-Chem is that Kepler-Chem resolves these images so that we don't have to worry about any of these stars being contained within the same pixel. So again, we don't have to worry about any of the light blending in with one another. In this image, the red kind of circle, or T1, is our TOI 2473 system, and T2, which is represented by the yellow circle, is the nearby eclipsing binary. And here is a full frame image of the field. And so the red points are just comparison stars. And here we are performing relative photometry. So in other words, we are comparing the brightnesses relative to these comparison stars. First, taking a look at the light curve around TOI 2473, we can see that it kind of has like a relatively shallow transit from the brown dwarf. And for each of these plots, the blue points represents the raw data, the black line represents the normalized spin fit, and the bright pink dots represents the comparison stars. And we kind of want this data to be essentially flat, because if they're not flat, this could imply that there's some weird signal coming from these comparison stars, so we wouldn't want to include them in our analysis. Here are the transit light curves around the nearby eclipsing binary, and we can see that it kind of has like a pretty deep depth of the transit, which makes sense given that this is an eclipsing binary. And so from these two uncontaminated transit light curves that were produced with Kepler-Chem with much better spatial resolution, we can therefore confirm that we have two systems. Specifically, TOI 2473 was a rare case in which, while the original test light curve showed that we might have two planets orbiting around the same star, we show that this is actually not the case, but rather the two different transits of 1.2 days and 6.5 days were a result of two different stars being located within the same test pixel, resulting in a false positive. Specifically, the 6.5-day transit was not part of TOI 2473, but was rather the result of light contamination from a nearby eclipsing binary. So our two systems in this case was the nearby eclipsing binary and TOI 2473 with the transiting brown dwarf companion. So now that we have confirmed that, we also want to better characterize the brown dwarf companion around TOI 2473, and I did this by using ExoFast. And ExoFast is an exoplanet transit and radial velocity fitting software, and what this means that I had to combine both the radial velocities as well as the light curves produced by AIJ. And just kind of like briefly running through how ExoFast works, we had to pass in 5 files, the radial velocities of the system, the spectral energy distribution of the system, which are the SED. The priors files just specifies any external constraints or starting values for the fit. This Kepler-Chem photometry is a result of when we create the light curves, it kind of outputs this really nice data that we also will want to pass into ExoFast. And the profile is what actually calls ExoFast and creates the fit. So from ExoFast, I identified the brown dwarf companion to have a mass of about 43.4 Jupiter mass and a radii of about 0.961 Jupiter radii. And in terms of the parameters of the host star, I found that it had a mass about 1.4 solar mass and a radii of about 1.5 solar radii, showing that this is an F-type main sequence star with temperatures around 6,500 Kelvin. So kind of to conclude, the purposes of my research was to confirm and characterize the candidates of the TOI 2473 system, and in doing so, I identified a false positive in the system in which the 6.5-day transit that was found in the original test light curve is not actually part of TOI 2473, but was a result of light contamination from a nearby eclipsing binary with a transiting companion with a mass of 0.21 solar masses. And that TOI 2473 actually only has one transiting companion with a period of 1.2 days, and this transiting companion is a brown dwarf with a mass of 43 Jupiter mass and a radii of 0.961 Jupiter radii. I would like to thank my advisors, Dr. Dave Latham and Alison Riorella, as well as Professor Naron and the entire Astro 98 class. Thank you for listening, and do you have any questions?
Thank you, Misha. Okay. We have time for some paradigmatic.
I was just wondering how unlucky this was. Has anyone worked out how often this will happen in the test paper?
I know that it's pretty rare, but I actually don't know the rate of how often this happens. But I can definitely look into that. We do have an expert, but I will get back to you.
Yes, there are papers on this. Yes, from 2011, because this was discovered in Kepler. The great discovery of Kepler that there were these compact systems in flat geometry with multiple transiting planets. It's really quite rare. Well, no, because it provided a junior project.
It did.
So, I want to make sure I heard the numbers right. So I think the separation on the sky between these two objects is about 40 arc seconds or something?
Yeah.
42.
That's two Kepler test pixels.
So what does that tell you?
Tells me that the PSF test is bigger than a pixel.
That's right. It would be dumb to have it be less than a pixel, right?
Well, yeah.
If you want to do good photometry.
So what is the point square function?
Well, it depends, but it's 2.5 pixels typically.
So it's not surprising that you get interference across that.
That's right.
Thank you.
Yeah, I was confused about exactly the same point. Because, you are very careful to say it's contaminated by light from this other binary. That's fine. So it can be on a different pixel. But in the beginning, you were constantly telling us two objects can be in the same pixel.
Yeah.
In fact, these two guys were not on the same pixel, right? One was on a neighboring pixel, but because of the PSF or whatever, the light was bleeding into this pixel's data.
Right.
Very nice. Okay. Okay. No other questions, Dave? No questions. Okay. Very good. Okay. So thank you, Michelle. Very clear talk. Wonderful.
Thank you.
Okay. Next, we will hear from Victoria Ono, who has been advised by Alyssa Goodman. Alyssa is not here. She's on sabbatical. So Victoria will tell us, well, her talk is, how do young stars leave home? And then she'll talk about velocity dispersions of two clusters.
So hi everyone, my name is Victoria, and this semester I was working on a project to study how young stars leave home, specifically studying the dispersion of young stars in molecular clouds with Professor Goodman. So I'd like to first start out with some background information to provide context for this project. The focus of this research was on molecular clouds and stars inside it, as there's still relatively a lot unknown about star formation and how stars are born as they evolve, especially in their younger stages. So molecular clouds, which are a component of the interstellar medium, are where stars are born. And within these clouds, they are star clusters, which are groups of these newly born stars, typically containing around a few hundred members. And these clusters are embedded in the molecular clouds at first.
And this phase lasts for around several million years, after which the gas is depleted by star formation or dispersed through other phenomena such as stellar winds or supernova explosions. So the disruptions of these clusters indicate the end of the star formation in that region. And this figure that you see on the right here is a figure that a member of Professor Goodman's group, also one of my advisors, Catherine Zucker, made. And you can see that there are different molecular clouds surrounding the sun, which you can see maybe not so clearly, but there's a little X indicating the sun. And so these clouds are all relatively nearby, just a few hundred parsecs away from us. And so this tells us that there's active star formation happening near us. And one particular cloud of interest is called Perseus, as we can see right there. So zooming in a little bit, Perseus has two main embedded clouds with active star formation, and they both, so NGC 1333 is the younger of the two at around 1 million years old, and they contain about 200 stars. And there's also IC 348, which has about 480 stars at around 2 to 6 mega-year-old. So these two clusters can be observed well in the optical region, such as this image shown right here. And they've been well studied to learn more about the star formation. And because one is older than the other, and they're both in the same cloud, it's also a great way to compare the behavior of the individual stars within each cluster. And NGC 1333 and IC 348 have been extensively researched by Professor Goodman and her group, which is why I chose to focus on them in this project. We wanted to explore, compare to the previous data and the results of these clusters measurements, such as the stellar velocity dispersions, how the improved data from Gaia may contribute to our calculations of the individual stars' coordinates and velocities. So the goals of the project, as outlined here, was to first visualize and analyze the data for 3D positions and velocities of the stars within these two clouds, then determine the 3D velocity dispersions of the young stars in these clusters, and then finally infer how much of those velocity dispersions is due to the measurement error or if it's actually due to the motion of the stars. And so we might be wondering, why are we focusing on the velocity dispersion specifically? Well, as stars grow and age, the distribution of the velocities changes from very closely together to broader as they eventually leave the cluster. And so we wanted to figure out whether the velocity dispersion is due to the errors or due to the errors that we were, with the instruments that we were using, particularly Gaia, or if it was due to the dynamics of these stars as they left home. So to tackle these goals, this was the outline of our methodology here. We first cross-matched the data. The most recent data release from Gaia was this past June. So we matched that with the radio velocity data that were published from 2 papers in 2015, Foster et al. For NGC 1333 and Qatar et al. For IC 348. And I applied the cuts to remove any of the stars that had large uncertainties in the radio velocity, as well as other different uncertainties outlined in those papers, as the velocity dispersions are quite small, and having any sort of larger uncertainties would affect the calculations of the velocity dispersions to a great deal. And then I calculated the 3D coordinates and the velocities using AstroPy. Then I fit a Gaussian distribution to measure the velocity dispersions along each dimension, as well as in 3D magnitude. And then finally, we used the data visualization tools and error analysis to study that dispersion. So this data visualization tool that I used in particular was called GLUE, which is an open source software library developed by Professor Goodman and her group. And this was particularly useful because it helps us link and visualize multiple data sets within each other. And this was perfect for our project because we had 2 data sets, NGC 1333 and IC 348, that we wanted to compare and analyze side by side over the common cloud of Perseus. And we already had the graph of the Perseus cloud, since they have been, the cloud has been studied particularly by Professor Goodman, and so we were able to overlay the data points on top of this gas cloud and see how the distributions compared with one another, as well as how they were located with respect to each other. So the first thing that we wanted to do was to visualize the coordinates. As you can see here, I was able to visualize the two clusters living in Perseus. So this first image shows from the plane of sky point of view. So we're looking at it from the perspective of the sun. The white fuzz represents the gas cloud of Perseus, and the cluster in pink is IC348, and the cluster in blue is NGC 1333. From this angle, we would deduce that the two regions are tightly clustered and all residing in the same area, but this is actually a 3D plot. So because this is perpendicular to the line of sight, we wouldn't be able to see depth. So we just see the two kind of like more in like a 2D formation. But because it's this plot is 3D, if we rotate the graph, it would look something like this. And now we're able to see that the clouds from the side, where this, the observer is, if we were looking at it head on from that, but now we're looking at it from the side, and we can clearly see the difference in the distributions of each of these clusters. And we immediately notice that there is a wide spread in distance for both clusters, but particularly more for NGC 1333. So seeing how spread out these stars are plotted on top of the gas cloud would allow us to explore the cluster membership for each cluster, and which is why this kind of 3D plot was particularly helpful. It allows us to wonder if some of these stars are actually part of the cluster as they have been classified in the past, because the stars that are farther away from the average distance would suggest that maybe they are not actually part of the cluster, even though they look like that in the 2D image that you saw earlier in the previous slide. So now that we saw how these are spatially distributed, we wanted to then find how they moved. So this was how we visualized the velocities. If we now look at them in terms of these velocities, we can see some interesting features. The stars in NGC 1333 are much wider spread out in their velocity dispersions, pretty scattered along each direction, whereas in IC348, most of the stars have velocities very close to each other. I wanted to point out that it may look like there's a lot more errors and bigger uncertainties for this graph on the right, but that was because we had a lot more data points for IC3048, so the error bars are kind of overlapping on top of each other. But NGC 1333 actually had some larger errors, which we wanted to explore more quantitatively now that we saw them visually. So what I did next was to plot the velocities along each direction over a histogram, and assuming a normal distribution, fit a Gaussian curve for each of these histograms and see how the distribution was spread out. And as we can see, the distributions are not very smooth. They're quite noisy, and they don't really look normal for ones particularly like the x direction, y direction, and you can also tell how broad these curves are. And you can tell that for NGC 1333, they're a lot noisier, and the standard deviations are a lot higher than the ones for IC3048, which is the bottom one here. And then now these two graphs show the histogram when we took the velocities in 3D, so just calculating the magnitude. And if we now look at them for each cluster, we can see clearly how the distribution for NGC 1333, which is the one on top, is more broad and uneven. This results in the former cluster having a higher standard deviation, which I denote as the velocity dispersion, than the other cluster. And we originally expected the distribution of NGC 1333 to be lower because it is a younger cluster, but there are several potential reasons for it exhibiting a higher dispersion, such as the fact that the sample size was a lot smaller, and that if we look at the right side of the histogram, you'll see kind of like a little bump in the histogram suggesting the idea that there may be a subpopulation within NGC 1333 that should not be actually in that histogram. And so if we focus on that, if we were to remove that part of the histogram, then the distribution would be much narrower and would exhibit a more normal distribution, which would result in a much lower standard deviation and therefore a smaller velocity dispersion. So that would indicate that the cluster didn't have all the right stars as they were classified. And so the next question to that would be, all right, well, where are all those outlier stars actually spatially there in the visual plots? So I did this by taking the uppermost bins for both clouds and plotted to see how where they were located in the visualized plots. And so here they are. For NGC 1333, we can see that the ones with the highest 3D velocity magnitude are those with the are pretty just scattered around. While for IC 3048, they're kind of all in the same vicinity, showing that for this cloud, that would have been due to the measurement error more likely, whereas for NGC 1333, it might suggest more of them having that subpopulation. And because that suggestion is there, we can kind of tell, all right, maybe now we can look at them how they are spatially and see if we can confirm that hypothesis. So this is, again, going back to the graphs spatially. And so if we look at it head on again, we wouldn't be able to speculate that those outlier stars are not actually members of the clusters, because they very much look like they're embedded together. But if we view from the side again, we can see that along the line of sight, the outlier stars are kind of the ones that are further away from the average distance. And so that kind of we can then further infer that they might not be part of the cluster. And that would suggest the difference between like the measurement error and the dynamics of the stars, which was the which was what we were trying to find. But because the sample sizes were small, one approach I made to see if this can be actually confirmed was to use an algorithm to help smooth out this data. So the method that I used to smooth out the data was called extreme deconvolution, whose purpose is to correct the distribution of noisy data, such as the one we have here, and assuming a Gaussian model again. After performing this, we can see a much tighter distribution for NGC 1333 and also for IC 348, but the corrected velocity dispersions were lower for both, but more so for NGC 1333. In fact, it was less by almost half a kilometer per second, while for the other cluster, it was just 0.13 kilometers per second, suggesting that indeed the dispersion for NGC 1333 would have been was affected due to this dip in the, not the dip, but the outlier stars. But clearly it is still higher than the one for IC 3048, so the question of why kind of still remains unanswered. I also want to quickly show this video. So this was the two clusters overlaid on top of the Worldwide Telescope viewer. So this is with the infrared sky background. You can see the two clusters, and if we show those outlier stars, you can tell for IC 3048, they're kind of just like randomly scattered throughout. But for for NGC 1333, they kind of show a pattern of them being in the lower right region. So that would also suggest that indeed they are not part of the cluster. So just to conclude and observe some takeaways, we were able to identify the cluster membership of each cluster by visualizing these coordinates in 3D to observe the depth, as well as visualizing the velocities and the velocity dispersions. And then we were, and because these velocity dispersions are very sensitive to errors and they were comparable to the uncertainties that were derived, further analysis does need to be needed to reject non-member stars. Some of the future steps would be to study clusters with larger available data sets and also clusters with larger ranges of ages and embeddedness, so that we can tell how the young stars at different stages move, and combining these findings would give us a better constraint on how the evolution of the stars in their early stages. I would like to quickly acknowledge Professor Goodman, Catherine Zucker, and Professor Narayan for taking on this amazing opportunity for me. Thank you.
Thank you, Victoria. We have questions. Yeah, Bobby.
Do you know how gravitationally bound are these systems, and if you try to estimate the time scale for evaporation?
Sorry, can you, could you repeat the question?
Yes. So, do you know how gravitationally bound are these systems, and if you try to estimate the evaporation time for the stellar component?
That's a great point that I didn't think about. Yeah, we didn't really think about how gravity might be affected or how gravitationally bound they were. Just based on their ages, the older one the stars were already kind of moving away, and the younger one was still confined within the gas cloud. That was kind of all the information that we were just working on off of.
I have a question on your 3D plots. So you are showing from the side view with the depth coordinate. I was wondering, what is the error bar on those measurements? I mean, the thing was so long. Is it mostly just the measurement error in terms of the depth?
Some of them were, especially for the younger cluster, but not all of them. So what we could also do is just see if the ones with larger errors would extend to the, like the contour of the gas cloud. But we haven't been able to clearly identify those stars.
Okay, right. Yeah.
How was cluster membership originally determined in the two papers that you referenced that define the clusters?
They were already, I think they were using the RA and Dept, so kind of how they were closely together. And there were also different kinds of, I think with where they were in relation to the gas cloud of Perseus and the, I think they were looking at the virial velocity and I'm not too sure. It's been a while since I read those papers, so I was mostly focused on how they applied the cuts to take away some of the field stars. I'm not exactly sure. I think it might have just been from the data project that they had already, which is from the Sloan Digital Sky, the InSync project that were published in 2015. So I think that might have already just been identified, and then those authors in the papers kind of used that and then went from there.
Very good. Thank you, Victoria. Okay, so next we'll hear from Jacob Bueller, who has been advised by Peter Maxson. So he's going to talk to us about a particular EGF, UGC 7342. Okay.
Thank you all for having me here today. My project advisor is Dr. Peter Maxson, and my project is about examining quasar accretion loads and X-ray luminosity in active galaxy UGC 7342. So this is a Hubble image of the galaxy we're looking at. There's a redshift of about 0.05, which corresponds to a distance of about 700 million light years. Most of the stars are within the central white cloudy region. There's a bright active galactic nucleus at the center, as well as the very obvious green extended gas that is the focus of a lot of this project. So black holes accrete matter from the disk around them. This causes relativistic jets, high energy emissions, and shocks, all of which can ionize oxygen within the extended gas in UGC 7342, which causes it to emit in the O3 wavelength, which we see as optically green, and it also causes a lot of X-rays. So these green clouds are known as Hanny's Vorwerp. The extended gas is a lot brighter than we would expect, given the infrared luminosity of the galactic center. Since the extended gas is up to 20 kilolight years away from the galactic center, we think it was ionized hundreds of thousands of years ago by a black hole that has since gone quiet. Sorry, I'm having an issue with my slide. So the project goal is to determine whether the AGN in UGC 7342 is undergoing a shutoff, and if so, to determine the magnitude of such a shutoff. This happens in 3 steps. The first one of which is to determine the X-ray luminosity of the AGN and the extended gas. The second is to compare the X-ray luminosity with the IR-based luminosity estimates made in 2012 by Keel et al. And the third is to conduct spectroscopy of the AGN in order to determine if it's obscured, and of the extended gas to determine its temperature. The significance of this project is that it will build our understanding of galaxy evolution. It will serve as another piece in the puzzle of understanding how quasar accretion loads change with time and how this affects the emission and large-scale structure of galaxies. So Keel et al. In 2012 examined UGC 7342 in the optical and far-infrared wavelengths and estimated, based on the extended gas emission, that the luminosity of the AGN about 10,000 years ago had to have been at least 4.4 times 10 to the 44 ergs per second. They also estimated, based on emission near the nucleus, that the present-day emission was 1.1 times 10 to the 44 ergs per second or less. That basically, their conclusion was essentially that the luminosity of the AGN dropped by a factor of at least 4 in the past 10,000 years. Dr. Maxim also wrote project proposals for NGC 5972 and UGC 11185, also estimating similar conclusions and proposing that they might vary on 10,000 to 100,000 year timescales. Next, I'm going to talk about our instruments. So we're going to be working with the data from the Chandra X-ray Observatory, which is NASA's premier X-ray telescope and has been running since 1999. X-rays don't like to reflect, so instead of a normal incidence reflecting mirror, like we would see for optical measurements, we use paraboloid mirrors to concentrate photons onto the sensor in a way that changes the photon's direction as little as possible. We're also going to be working with the ACIS BI chip, which is effective for photon energies between 0.3 and 7 kilo electron volts. It reads out every 3 seconds, which is typically fast relative to the number of photons you get in X-ray astronomy, because you don't get that many photons in X-ray astronomy. So every photon you see will typically be the only photon in that pixel. And as a result, you can easily get the energy of the photon from the number of electrons that come out of the CCD. This means that we don't usually have to scatter light using a spectrograph in order to understand energy distributions. Next, I'm going to talk about our methodology and our results. Step 1 is to reprocess our raw images, which means correcting for observing errors. In this slide, we see the bias, or the innate measurement error of our chip, which we have to correct for. We were working with 3 sets of observations, each created on different nights. Chandra's orientation shifted between these measurements because it moves in a dithering pattern, or a figure-8 pattern. We need to make sure these measurements are actually properly aligned. If not, we get errors like we see on the right, with the same X-ray source is recorded as being in 3 different locations. You see it as blue, green, and red. The next step is to bin photons by energy. And we can actually choose specific energy ranges to examine. Comparing the left and the right-hand pictures, you can kind of see the difference between the broadband on the left and the hardband on the right X-ray measurements. The active galactic nucleus is what we're pointing to in both of these pictures, and it stands out a lot more on the right side because it is really one of the only types of hard X-ray sources in the universe. Additionally, different energies correspond to different physical processes. 6 to 7 kilo electron volts corresponds to iron emission, which would be a really unusual and really interesting result. Energies below 3 kilo electron volts typically correspond to thermal emission from hot gas. next I'm going to talk about how this might be applicable to our project. Generally speaking, dust blocks X-rays of energy below 3 keV. And because black holes are typically surrounded by these accretion disks, which are made of gas and dust, we believe that any X-rays that we receive of energy below 3 keV are probably coming from the extended gas and not the black hole. And by contrast, X-rays of energy above 3 keV are probably coming from the black hole. Next, I'm going to talk about luminosity estimates and how we got them. So first of all, we select the region of the galaxy that we actually want to look at. In this case, on the top right, we're looking at the extended gas, and we're excluding the central AGN. We also make sure to, bin for the band that we're actually looking at, and that could be, that could be 0.3 all the way up to 7. But it could also be any subset of that. This gives us a photon count rate, which you see, in the statistics readout above that image, which we can convert with a tool developed by Chandra into an actual luminosity estimate of the extended gas and of the central black hole. And note that the bolometric luminosity is generally 10 times higher than X-ray luminosity alone. Next, we're going to compare our estimate of the present-day AGN luminosity that we calculated in this project to other authors' estimates of historical AGN luminosity. We use the highest estimate of present-day AGN luminosity to get a lower limit on the shutoff magnitude. Bolometric luminosity is 10 times higher than X-ray luminosity alone, so we estimate a present-day bolometric luminosity of, at most, 1.02 times 10 to the 43 ergs per second. Keel et al. Estimated, based on optical measurements of the extended gas, that the luminosity of the AGN 10,000 years ago had to have been at least 4.4 times 10 to the 44 ergs per second. And this leads us to the conclusion that the active galactic nucleus is at least 40 times dimmer today than it was 10,000 years ago. We'd also like to make signal-to-noise ratio estimates for the extended gas. We actually looked at the extended gas emission in specific bands in order to see whether there was that narrow band emission that would suggest either low-density hot plasma, which corresponds to 2 to 3 keV, or extended iron excitation, which would be 6 to 7 keV. And the truth is we actually found no evidence for this, and the signal-to-noise ratio is very low in those bands. We definitely didn't expect to see that. We actually found that the extended gas is hard to detect in any X-ray band, even 0.3 all the way up to 7.0 keV. This could either be due to a lack of measurements. It could also just be that the extended gas just isn't that bright. So in conclusion, Keel et al. Estimate based on the extended gas, the luminosity was once greater than 4.4 times 10 to the 44 ergs per second. They also estimate that the bolometric luminosity is now, at most, 1.1 times 10 to the 44 ergs per second, based off far infrared measurements of the galactic center. However, we estimate the bolometric luminosity as now being, at most, 1.02 times 10 to the 43 ergs per second based on X-ray measurements, which are probably more accurate because less celestial objects produce X-rays as compared to infrared. This means that the luminosity has dropped by a factor of at least 40. Keel et al. Estimated a factor of 4, so this is actually an update on that. The caveat is that we don't know the column density of the interstellar medium. We estimated a Compton-thick obscuration, which basically means that the thick as it could reasonably possibly be. If the column density is lower, then the variability would be more dramatic. We do detect the active galactic nucleus in X-ray bands, but not the extended gas. This doesn't tell us anything about the variability, but it does say something about the gas, and that's that the gas in this extended region has a high O3 to soft X-ray ratio. And that means the O3 emission is probably tracing dense gas that's not associated with the wind, but rather in filaments of gas in the galactic plane. And the reason that this is true is because the ratio is a density-dependent effect. And deeper X-ray observations would get us a better handle on the nature of the extended gas. I think I skipped a slide. Can I go back? Yeah, it's really awkward. Yeah, okay. That's my bad. The next step is to calculate the ratios between the luminosity from O3 emission and the luminosity from soft X-ray emission in different areas of the galaxy. and to compare these with existing studies. From Hubble optical measurements of UGC 7342, we estimate optical-only luminosities of 2.3 times 10 to the 41 ergs per second for the active galactic nucleus, and 8.1 times 10 to the 41 ergs per second for the extended gas. Given our previous X-ray measurements, this gives us an O3 to soft X-ray luminosity ratio of 16 for the active galactic nucleus, which is consistent with work done by Fabiano and Elvis. This also initially gives us a ratio of about 45 for the extended gas, but because the signal-to-noise ratio of the extended gas measurements is so poor, its X-ray luminosity could be 3 times lower or higher. So the O3 to soft wave X-ray luminosity ratio could actually be anywhere from 15 to 150 realistically, which is a lot higher than Fabiano and Elvis predict. If we visualize these measurements by overlaying them on this graphic, which shows how the ratio evolves as you move out from the center of the galaxy, we find that the O3 to soft X-ray ratio in UGC 7342 increases more quickly than we would expect. This could be the result of measurement error, or it could be a legitimate result that indicates that the outer regions of UGC 7342 are actually denser than we expected, which would indicate that most of the O3 emission is coming from large-scale filamentary structures within the extended gas. All right. Yeah. No. Okay. And so as for our next steps, there are 3 main next steps that I think I want to explore. The first of all is to conduct spectroscopy on the active galactic nucleus. We want to determine lower limits for the column density that would help us to estimate upper limits on the current bolometric AGN luminosity. And once again, we would compare this with the Keel et al. Estimate of the historical AGN luminosity to constrain lower limits on variability. Again, right now we have a very conservative lower limit on the variability, but if the column density is actually lower than we expect, then the current X-ray luminosity is also lower than we expect. This would mean that the ratio between the active and inactive luminosities, and therefore the variability, is actually higher than we calculate here. The next step would be to present at AAS 241 in Seattle, which I'm very excited for in January. And then the third step, which I talked a little bit about before, would be to conduct more extensive X-ray observations of the extended gas to determine whether the poor signal-to-noise ratio of our X-ray measurements of the extended gas is a legitimate measurement, and that it's actually just not that bright, or whether that's just because we didn't measure it quite enough. So I want to give a very special thank you to Dr. Maxon for his leadership and for making this project possible, to Professor Narayan for guiding the entire class, and of course to my Astronomy 98 classmates for all their support and feedback.
Thanks, Jacob. Okay, we have time for some questions. So I had a question. There is this Keel et al. Estimate of the luminosity, current day luminosity, which was like 10 to the 44 ergs per second. You came up with another estimate of the luminosity, which is 10 times less, right? You're saying it's less than 10 to the 43. So that factor of 10, is it that it's not that they measured it wrong, right? You're saying that what they measured is not just the AGN, but they were confused by some other source of infrared. What is the reason for this factor of 10?
Yeah, that's probably a good reason as to why. That's probably the most plausible explanation. Yeah.
Something else was radiating.
Yeah, there's a lot
of luminosity.
Absolutely, yeah. There's a lot of stuff besides the AGN that could be causing that infrared luminosity. Stars don't really emit like X-rays, but they will emit like far infrared. Even gas, that's not that hot will emit far infrared, but not X-rays, for instance.
Right. So your claim would be that your X-ray measurement is the number to take. That's more reliable.
Yeah, exactly, yes.
Okay, good. See, X-rays are good.
Awesome.
We knew that, of course, yeah. Very good. Okay, there's a question there.
So just a kind of a follow on. So the first measurement was like 4.4, then they measured 1.1. So you're saying that one's incorrect, slightly wrong. Is the 4.1, 4.41 also slightly incorrect?
The 4.41 we think is probably pretty correct. So basically, yeah, the 4.4 times 10 to the 44 is like Keel et al. Estimated in 2012, 10,000 years ago, that was how bright the AGN was. And we're still, like, for the purposes of this project, we consider that to be pretty correct. And yeah, that's based on like optical measurements of the extended gas. And then the 1.1 times 10 to the 44 is based on their far infrared measurements of just the nucleus, which because it's not very specific, we're updating here and saying that actually we believe it's probably closer to, or we believe it's at most like 1.03 times 10 to the 43.
So could it just be the black hole was dimming, and so like they just caught it, closer to the peak and then it dropped off, or is that kind of like it dropped off far too quickly for that?
Well, we think the black hole would have taken several thousand years to dim, but we would have thought, so I think just that it was probably the same black hole. It was probably behaving the same when they took their measurements, but it's just that we think that our measurement might be a little more specific because it's tracking only the radiation that's coming from the AGN and not the stuff around it.
Great. Thank you, Jacob. Okay, now our final speaker, Emma Weller, who has been advised by Fabio Pacucci. So she's going to talk about overmassive central supermassive black holes, and she's going to describe work done using big simulations, TNG50 and Astrid.
Hello, I'm Emma, and I'm presenting about overmassive central black holes in the Astrid and illustrious TNG50 simulations, and my advisor is Fabio Pacucci. And this work is motivated by the Leo 1 dwarf galaxy, which is a satellite of the Milky Way. And this paper, about a year ago, did dynamical analysis on the galaxy and found that it has a black hole of about 3 million solar masses, which is very surprising because its stellar mass is only about 50 million solar masses. And for comparison, the Milky Way has a black hole, central black hole of about the same size, but its stellar mass is 3 orders of magnitude larger. And so here, shown here is the MBH-M star relation between black hole mass and properties of the host. And the star here represents the Milky Way, but then Leo 1 is all the way over here. And so the goal of this project is to understand how a galaxy like Leo 1 could form with such an overmassive central black hole. So the first simulation that I used is TNG50, which is the highest resolution run of the illustrious TNG project. And for this project, the useful part about this simulation is that it has subhalo merger trees, where subhalo is the galaxies in the simulation. And so we can track the evolution through time of properties of the subhalos. However, the seed mass in the simulation is rather high, about 1 million solar masses, which can cause problems for certain types of analysis in this work because, for example, if we're interested in the fraction of small galaxies that have overmassive black holes, in this simulation, any small galaxy that has a black hole is going to have an overmassive black hole just because of the seed mass. So then the other simulation that I used is Astrid, which is a new simulation that hasn't finished running yet, but it's currently to redshift 0. And this one is useful because it has a lower seed mass, which alleviates some of the problems I just described. But it doesn't have subhalo merger trees, which makes it harder to track through time the evolution of a large number of galaxies. So here I have a plot that kind of combines everything I'm using. On the y-axis is central black hole mass, and on the x-axis is subhalo stellar mass. And so then the points represent galaxies in the two simulations. So blue is Astrid, purple is TNG50, and then I've marked the medians and IQR, interquartile range of the data for each simulation. And then a couple other things to note here. I've marked the seed mass or seed mass range for each simulation, so we don't have any data below that. And then in orange is the MBH-M star relation from the review by Corman Yin Ho. And then the last thing here is we see that asteroid covers a much larger mass range. And so we actually have galaxies that are quite similar in black hole and stellar mass to Leo 1, which is marked in red. So starting with TNG 50, as I said, this is a good simulation to use for subhalo evolution, and it's run up to redshift 0. So all of the purple data in the plot here is the mass is at redshift 0. For these galaxies we're studying, it only has one supermassive black hole per subhalo because they are so large. We don't have any small galaxies, and so that makes it really easy to pick the central black hole because there's only one, and they're positioned to be at the center. But then because we don't have a lot of small galaxies that host black holes in Illustris, we have to look at slightly larger galaxies. So the first thing that I did is picked a black hole mass of around 10 to the 7, and then said for this black hole mass, for galaxies that have a black hole of around this size, let's look at some that are particularly small so that they have overmassive black holes, and then some that are right on the red or the M sigma relation, MBH-M star relation, at redshift 0. And so here I've shown the tracks of 4 galaxies that end up with significantly overmassive black holes, and then 4 that end up on the M sigma relation at redshift 0. And so they start off all at around the same mass, that's the seed mass, and then end up at around 10 to the 7. But what we can see is that the orange galaxies, which are the ones that end up with overmassive black holes, diverge from the M sigma relation pretty quickly. That's shown in green here, while the blue ones follow that relation the whole time. And then another thing to note is that these orange ones, the average redshift at which the black holes start getting tracked in the simulation is 1.6, and it's about 2.2 for the blue galaxies, which means that the blue galaxies have existed for longer. And so that means that they're growing, the black holes are actually growing slightly more slowly since we had the same change in black hole mass. So in the following slides, I'll try to explain possible reasons for why the stellar mass is growing so much slower for the orange galaxies, but the black hole mass is growing slightly more quickly. So the second thing that I did in TNG 50 is looked at a larger population of galaxies between 10 to the 9 and 10 to the 10 solar masses, the ones shown in the oval here. And we want to compare the evolution of galaxies with overmassive and undermassive black holes. But as you can see in this plot, Illustris has a lot more galaxies over the MBH-M star relation than under in this range. And so to get a more even number above and below, we took this data and fitted a best fit line to the log of this black hole mass versus stellar mass, and that's shown in the blue line here along with the medians. And so we said that any black hole above this line is overmassive, any black hole below the line is undermassive, and any black hole on the line would be on kind of our average. And so we define this parameter C to quantify that, which is the log of the black hole mass over the mass that we would expect based on the best fit line, where C greater than 0 is undermassive, C less than 0 is, C greater than 0 is overmassive, and C less than 0 is undermassive. And so with that in mind, looking at the growth of the central supermassive black hole, we wanted to be able to study a large population over the same time range. So I chose a period of about 55 snapshots, or 8.7 gigayears, and then excluded any black holes that hadn't been tracked in the simulation for that long. And I have the plots here. So what we can see is there's not a huge difference. These are the medians, and I plotted it as a fraction of the initial mass just so that it's comparable, so they all start at 1. And there's not a huge difference. The interquartile ranges actually overlap. But again, we see that the C greater than 0, so overmassive black holes, are growing slightly more quickly. And if we look at the fraction of the black hole mass for C greater than 0 versus C less than 0, we see that at the beginning they're about 1.6 times larger on average, and at the end, at redshift 0, they're about 1.77 times larger. So then next, we wanted to look at the growth of the subhalo stellar mass, which from the tracks, we saw that
subhalo stellar mass grows significantly more slowly for the galaxies with overmassive black holes. And so again, we look at this over the same time period, and here's the plot. And here we can see that the undermassive black holes in green, their host galaxies, are growing significantly faster, while the galaxies with overmassive black holes in orange are growing more slowly. And looking again at the fraction of stellar mass for overmassive versus undermassive, we see that the galaxies with overmassive black holes tend to start out a bit larger, but by redshift 0, they're smaller. And so the question then is, why are these galaxies growing so much more slowly if they have an overmassive black hole? And one possibility is that if they have a larger black hole, there's more black hole feedback, and that's inhibiting star formation. And so we looked at the star formation rate for all of the galaxies in this sample. And so on the left, C less than 0 is undermassive black holes, C greater than 0 on the right is overmassive. And we do, in fact, see that the star formation rate is higher for the galaxies with undermassive black holes, which confirms that idea. So then turning to Astrid, the nice thing about this is that I can actually look at galaxies that are quite similar to Leo 1. But because it hasn't run all the way to redshift 0 yet, the furthest I can go is redshift 2. So all this blue data in the plot here is taken at redshift 2. And then sometimes there are multiple black holes in a galaxy since they're smaller in this simulation. So we take the largest black hole to be the central supermassive black hole, which generally works well because it's usually several orders of magnitude larger than other black holes in the galaxy and pretty close to the center. So what I've done here is I've taken 4 galaxies that are quite similar at redshift 2 to Leo 1, and I've looked at them. So each pair on the left is redshift 3, and on the right is redshift 2. And so I've shown all the stars around the black hole of interest. So the black hole of interest is marked as a blue X at the center of each plot, and then other black holes are red X's, and I've highlighted in green the stars that belong to the host galaxy. And so what we're seeing here is that the host galaxy starts out significantly larger, but then it interacts with an even bigger galaxy and loses a lot of its stellar mass by redshift 2. So this could explain another reason, or another way in which the galaxies with overmassive black holes are losing stellar mass to end up that way, is that they're being tidally stripped by larger galaxies. And that could explain why in the tracks I showed at the very beginning, where I showed those 8 galaxies, some of them actually went backwards at the end, so they lost stellar mass. That could explain why that was happening, and is also a plausible situation for Leo 1 because it is a satellite of the Milky Way. So in summary, we find that the overmassive central supermassive black holes grow more quickly, which makes sense because they're larger, and that the galaxies with overmassive black holes have significantly slower stellar mass growth, which is likely due to a combination of lower star formation rate and interactions with larger galaxies that lead to tidal stripping. Thank you.
Thank you, Emma. Okay, we have time for a few questions. Charles?
I wonder what really to take away from this about Leo 1, because Leo 1 still seems to be very much an outlier in everything that you've done, right? Because your conclusions are very interesting, but they don't seem to be extreme enough to account for Leo 1. Is that fair?
And these end up very similar to Leo 1. Their stellar and black hole mass are fairly comparable to Leo 1.
Okay, so thank you.
Yeah, and in the plot I showed before this, Leo 1 is marked in red, so there are several galaxies that are similar.
But within the asteroid points, Leo 1 is it's good that it's on the plot, but it seems to be the very large number of galaxies below it.
Yes, yeah, it's definitely an outlier, and not the most common case, but there are galaxies that are like it. It's just there's not a lot of them.
Yeah. So I think to Charles's point, This guy was a big surprise when it
Yes,
showed up.
yeah.
It's still a surprise, but you're saying it's not impossible, it can happen.
Yes,
That's
yeah.
really what
Or
this
at
is.
least we were able to find similar cases in the simulation. But of course, that's only a couple cases out of a much larger population.
Right. And for the particular cases near Leo 1, you have followed their entire history to see what they did?
These ones here, it's as I said at the beginning, it's a bit hard to track their entire history in Astrid because there's no subhalo merger trees. So to do this, you actually have to kind of look for a galaxy that hosts the same black hole. And it's just a bit challenging to do for a large number of snapshots, which is why in these plots I only have redshift 3 and redshift 2. It's hard to make plots like I had for Illustris.
But is Astrid going to make merger trees in the future?
I'm not sure.
That would use it and actually follow the track of your systems.
Yeah, that might be planned once it finishes running.
Mm-hmm. Yeah.
Yeah.
Okay. Oh, this question then, yes.
I was just wondering, what's the masses of these galaxies that are stripping the smaller galaxies? And are they comparable to like the Milky Way or something?
That's a good question, which again, it is a bit difficult to calculate because I don't have the merger trees. I think that they are, I don't know the exact mass and how comparable they are to the Milky Way, but they are significantly larger as we can see from this. Yeah.
This is really awesome. Can you comment on the scatter of Astrid versus it looks like in G50 the scatter of black hole mass is much smaller.
Yeah, so because the black holes are so large in Illustris, there's just fewer galaxies, especially on the small end, that host large black holes, which is why there's just a much smaller range. As far as actually quantifying the scatter, I'm currently working on that, and it will be in the paper, but I haven't quite finished that analysis yet.
I see. So essentially it's narrow because all these black holes, they grow from very massive seeds and you need very low mass seeds to produce the dark sky. Okay, yeah, I got it. Makes sense. Thanks.
Yeah.
Very good. Okay, thank you, Emma. So let's close the program here. We thank all the speakers. I think they are excellent speakers, that we can tell. And I just get a shudder to think what I was like when I was at that age. I don't want to speak like this at all. And of course, I knew nothing about PowerPoint. And we invented. That's the reason. But also, I want to thank the audience. Thank you all for showing up. Watch out for these young people. You know, they are going to go on and they are going to make CFA famous in the future. Okay? So well done, class. Well done.